We're going to start looking at logistic growth or logistical growth. And as you look at this, your mind is going to wander back to the good old days of exponential growth because you remember many times in your math classes investigating things that would start growing and then grow at an ever increasing rate. Well, logistic growth is going to kind of be the cousin of the old exponential growth. And what we're going to do is we're going to kind of model what would happen a lot of times in a population, where in the beginning you started with some exponential growth, but then if you think about it in reality, exponential growth can't continue on to infinity for many different things. So at some point, let's say there's a certain disease spreading through a population. It may be growing very rapidly for a while, but then eventually there's not much more room to grow, and so the population or the number of people infected with the disease begins to level off at some sort of population limit. So what you're looking at here is logistic growth, which looks in the beginning very much like exponential growth, but then has a natural cap. Now, I used an example of a disease spreading through a population. There's plenty of biological applications for this, but if you move on into big boy economics and things like that, you'll find many other ways that logistic growth shows up in this world. Flipping back to exponential growth for a second, we had a very juicy equation for that, y equals ce to the kt. You're familiar with that from many math courses. But what you may or may not remember from your good old calculus course last year is there was a differential equation, dy dx equals kx. This was differential equation talk for that same phenomenon. Since this is so famous, that's what's in your brain, but at one point we solved this differential equation and got that. Okay, well, let's go back to logistic growth. Logistic growth has a not so famous original equation, but a very famous differential equation. And there it is. It's a differential equation, and let's take a look at this because understanding the concept behind this equation is really going to help make sense of this phenomenon when it gets more complicated. dp dt, the change in population over time. Well, I could just think of that as a growth rate. All right, now we see a k in there. That k, if you were back in the old algebra days, they might say this is a constant of proportionality. That's a fancy term, but you know that's just some sort of constant. So now the growth rate is proportional to this thing, and now we need to take a look at what's going on there. So I've paused the video to take time to write this in. So what's going on here is we're multiplying the current population level, p, that's a value on the y-axis, and then we're multiplying it by the difference between the ultimate limit and the current population, or how much space does the population have to grow. So essentially what we're looking at here is a growth rate is proportional to, in some way, shape, or form, how far away the population is from its ultimate limit. Putting that sentence into your brain gives you a really good intuitive feel for what the logistic growth differential equation represents. You may want to pause that to write that down or install that permanently into your brain. And just a little side note before we move on, this is the differential equation that represents logistic growth. If we would solve that just differential equation, we would get some sort of P of t equation, a population equation. That's going to be a bear to solve, so we're not going to worry about that right now. What we're going to do is move on and do a little bit more analysis of this so that you can build some intuition. So I've taken our general logistic growth differential equation and I've filled in values for a real example. So this is the constant of proportionality. And as I look at this, I can already tell that the limit of the population, whatever population we're talking about here, it's not going to exceed 300. So that's our population limit. Well, if I evaluated dp dt, I can plug in any population I care about, and I can find out the growth rate of my population. So in the case of dp dt equals 10, I plug in the numbers, do the math, and I get a growth rate of 870. So in other words, when my population was very small, 10 must be a pretty small population, I have that growth rate. Now if I think about how logistic growth goes, that would be kind of like saying we're right about at this spot. So I'm just going to pretend we're going to say that is a population of 10. Notice that to make the evaluation of the growth rate, I'm plugging in a population value, not a time value. That's kind of weird. I'm plugging in a y value to get out a growth rate value. And what that 870 would represent is, since it's the growth rate, it's the tangent line at that spot. So when the population was 80, I'm just making stuff up here, so let's just say that would be about right here, we would anticipate quite a larger growth rate. So let's find out what that is. And as we would guess from intuition, the growth rate when the population was 80 is much greater than the growth rate when the population was 10. And as Homer Simpson would say, math checks out. Okay, so now our population limit was 300. So in this case, I can estimate that on my crude graph here, that this is a y value of 300. And the growth rate of the population, or in this case, a disease going through the population, should be leveling off as the population, as the amount closes in on the limit of 300. So for example, if I was up here, let's say that population is 290, we would anticipate a very tiny growth rate. And as we would suspect, the growth rate is very, very tiny. In fact, you can tell since we're 10 units away from the maximum, and here we were 10 units away from 0, it's a symmetrical type of situation. And that's just telling me as my population approaches its limit, its growth rate is getting very, very small again. I've taken the time to put that logistic growth equation into my calculator, and I'm going to graph it, and I'm going to get this graph. Oh, wait. I'm going to get this graph. And it's important to know the relationship between the graph you're looking here, the graph of my dp dt equation that I've covered up, and this graph right here. This is the population graph. Its slope, or its growth rate, or its derivative is this graph. And that makes a lot of sense because if you look here, it's a slightly positive slope, slightly positive derivative value. Very steep slope, still positive. The derivative value is a high positive y value. And the derivative's y values are returning back towards small positive numbers because the slope is turning back into small positive numbers. Homer Simpson would also say math checks out. So as you may have been picking up on, this logistic growth, which is a really good application of math onto the world, is also a playground for calculus professors or AP test writers to test your calculus knowledge. Because you may have been picking up on the fact that there's a lot of curve sketching possibilities going on here. This is an original function. We had just looked at a derivative graph. There's points of inflection, increasing, decreasing, maximums, minimums, all sorts of stuff. Also, there's some limit thinking. We have a horizontal asymptote. We have quite a bit of limit stuff going on in here. This is obviously a differential equation that could be solved to turn into a regular equation. You're going to find out that this ends up becoming an opportunity for some algebra trickery because this equation is not always given to you in that form. And as you're doing all of this, remember that this is happening over time, but yet there's no t in this equation, so you end up with derivatives with respect to time or implicit differentiation. There's going to be a lot going on, and it all boils down to this basic concept that the change in the population, or the growth rate of the population, is proportional to the difference between the population and its eventual limit.